for lack of a better name, DNS Explained. Please welcome Lynn.
Can you, oh hey, you can hear me. I just have to take a picture of y'all and tweet about it because it's amazing to see this many people just as confused about DNS as I am. All right. So yeah, I am Lynn Root. Let's see, getting myself organized here. So yeah, I am Lynn Root. Oh, there's no slides. Just kidding. I work for Spotify as a partner engineer. Whoa, that's really bright. Good morning. I'm also a founder of PyLadies of San Francisco. I do a lot of organization for workshops and speaker series and stuff like that. And if you want to start your own local PyLadies, it should be you should be able to just pip install PyLadies and get your own handbook. Yeah, and I am also board member of the Python Software Foundation. Awesome. So yeah, cool. Let's get this started. As a nerdy person who likes to jet away to I don't know, a hotel an hour away and do some hacking over a long weekend, trying to deploy some cool little app, I always seem to mess it up, right? A simple git push to Heroku doesn't work. Who's ever had that issue, trying to deploy something simple, git push? Yeah. Your friend can't see it? Yeah, okay, I see a lot of hands. I'm sure you recognize this. It's always a DNS issue when you're trying to deploy your app. And I'm sure none of you here have had a clean DNS setup the first time around, otherwise you would not be here. Who has had a very clean setup, a DNS setup first time around? No? Okay, oh, one person. I don't know why you're here, then maybe you should give the talk. So you follow instructions to properly set up your DNS records, and something doesn't work, and we've all been there. And so without a solid understanding of DNS, and sometimes folks just I'll just try this, and I'll just tweak this record or something like that, waiting for DNS to propagate to see if your guess was correct. So hopefully this presentation will give you a better understanding. Curiosity got the best of me when I was git push trying to deploy, and it didn't work. I wanted to sort of dive deeper into what DNS is. I knew that DNS was considered the phone book, and it's the backbone of the internet, but I also knew that the cloud is built on DNS and duct tape, and DNS itself is pretty much duct taped together. So while it is confusing, it has a textbook sort of definition, but it doesn't always work the way we think it does. So what I'll exactly be going over is what DNS is and why you should care about DNS, what to do with it, what to do with DNS, as well as awesome things I learned along the way. So first, I want to explain why DNS is important. It allows you to visit very productive websites like Reddit. It allows you to receive very time-critical emails like Groupon or Guilt. Deploy your one-of-a-kind to-do app on Heroku. And it allows you to, for your corporate meme generator, to not be accessible by non-employees. So we know that DNS is essentially the phone book. It stands for Domain Name System and translates from human-readable names to computer-friendly addresses. But the actual textbook definition is that DNS is a distributed storage system for resource records. Each DNS resolver or authoritative server stores these records in its cache or a local zone file. And a record usually contains a label, a class, type, and some data. So that might be the textbook, but that still, you're right, all right, I kind of oh, sorry, I'm kind of behind. It kind of still doesn't make sense. You get it, but you don't actually get it. So let's actually see DNS in action. So in order to understand DNS, I was playing with Python, of course. I used Scapy to sniff some DNS traffic to browse the interwebs. So I'm using Scapy to sniff, like Scapy's sniff function to pick up my local traffic. As you can see, I've filtered my traffic via UDP and port 53 just to hone in on DNS traffic. And I've only limited to like 10 packets. So as I let this sniff function run, I went to type in my browser, roguelyn.com, which is my website. Really cool, you should see it. What's pretty cool is, that I found that you can kind of see here is I was typing roguelyn.com into like my Chrome address bar, and a DNS query would take place for every autocomplete guess that Chrome took. So first, it pings google.com because the address is also a search function, right? And then as I type R, it autocompletes to Reddit because I kind of go there very often. And then you can actually see the DNS query on the second line for Reddit. And then as I type RO, Chrome guesses roguelyn-spy, which is my super awesome How to Spy with Python presentation that you should check out. And then we can see its related query that it points to on the fifth line. And then it finds roguelyn.com once I type ROG and press enter with Chrome's autocompletion. So I guess that's more of a cool thing about Chrome than DNS, but I still think it's pretty cool. But one thing that you might notice here, and I'm not sure if you can really see it, but all these DNS queries have a dot at the end. And I'm sure that many of you know that it's like just how DNS does things. But does anyone know like why it's there? Raise hands. Got like 3. Okay, good. You're in the right place. So the difference between a dot and a no dot is basically the same difference between an absolute file path and relative file paths. So like relative file paths, it can be like this /static can be mangled or mapped incorrectly. So depending upon how your local DNS is set up, if you have search example.net in your resolve.conf and you navigate to example.com, DNS search query will take the URL not to be fully qualified, and therefore will look up example.com.example.net or whatever. You can see that if I actually search for example.com it will go to example.com, not that example.com.example.net. So if there is a dot at the end, then it's an unambiguous, fully qualified domain name, and it's not prone to search path spoofing. Now, I didn't put a dot while navigating to Roguelyn, but putting a dot is not exactly user-friendly when you're trying to like type in something. So Chrome kind of inherently assumes a dot. So handling all this DNS stuff, all this DNS querying stuff, kind of got me curious, as one is. And I wanted to figure out what route the DNS query takes to finally get an answer for where Roguelyn is hosted. And it's not actually that easy to figure out. Once the DNS query hits the router, it's a bit of a black box, and the query is forwarded to if it's not locally cached. I know that my computer's DNS is set up to 192.168.11, which is my router, and my router's DNS is set up to 75.75.75.75. And I found this out by actually logging into the admin page of my router. So if I do a host query for the router's DNS, I can see that there is a pointer to a Comcast.net subdomain. Now, if I do a whois query on that IP, I see that Comcast, my ISP provider, actually owns the IP address. But beyond that, I do not know if Comcast's DNS has roguelyn.com cached, and if not, I don't know where it goes to get that information. But DNS, as some of you might know, is hierarchical, and getting familiar with the dig command can help us understand that sort of hierarchy and how queries are resolved. Dig command actually has this nice trace flag that makes iterative queries to resolve the name being looked up. It follows referrals from the root server, showing the answer from each server that was used to do the reverse lookup. So if we try that out with python.org, you can see I use the dig command. I apologize if it's too small. I did the dig command against python.org with the trace flag, and you can kind of see like a barf of information. But let's look at it in a prettier representation. So the query actually starts from my local DNS, 192.168.1.1, where if not cached is passed on to the root server, which is just dot. The query from my local DNS for python.org first asks for the root server, the dot, who knows that one of these hosts should have that, the information, one of those hosts there. And so the name server responds with, go ahead and try one of these, which corresponds to a .org name server. And so .org name server receives the query and then says something like, try one of these hosts, which corresponds to the python.org name server. And now the python.org name server says, yep, I have an A record for python.org, which is 140 to 11.10.69. So we successfully resolved python.org, but you can see we have like other like subdomains. If we wanted to know more about, say, like hg.python.org, we can do a dig command, and we actually see that it's a CNAME record mapped to a record that's owned by Oregon State University's open source lab, which is a different record elsewhere. So now I'm sure that python.org has more records than just NS and A records. So if we're curious, we can run the dig command with the -t any. Unfortunately, we only see A records and NS records. But if we look at pyladies.com, it's a little bit more interesting. You can see SOA records pointing to name.com. You can see our mail records, our MX records, pointing to Google, and A records pointing to our web host. What you don't get is with any is the full zone file or the DNS setup, like all the CNAMEs that are possible. And I'll actually go into that a little bit in a few minutes. But moving on, so we can easily see how DNS, like that path, takes for resolving python.org. However, it's not the most efficient way for DNS to respond to queries. The root and the top-level name servers like .and .org would be inundated with requests if our DNS resolvers always go to the start. And so that's where DNS caching comes into play. And so when a DNS resolver or authoritative name server receives a query, it searches its cache for a matching label. If there is no matching label in the cache, the server may instead retrieve from its cache a referral response containing a resource record set of NS records for a label that might be closer to the domain, which is the subject of the query. So instead of receiving a referral response, a DNS resolver can also be configured to initiate same query for an authoritative DNS server responsible for the domain name, which is the subject of the query. The authoritative name server can respond with an answer, referral, or failed response. The authoritative name server's response is accepted by a DNS resolver and then is subsequently stored into cache if it only meets certain conditions, which is specific to the resolver's implementation. So if my local DNS server's cache was completely empty, I could send a DNS query for python.org to the root server, and then get pointed to go to the name server to handle the .org domain. But it's more likely that I have something like .org sites already cached, so I can go straight to like the .org sites. And then it just kind of trickles down from there. DNS caching is all great and hunky-dory until you get to propagation. Propagation is how long one has to wait for DNS changes to show effect. And a DNS record will hold an item called TTL, time to live number, at which point it deletes it if that time to live is up. So after it's deleted, if someone makes a new request that refers to that record, the DNS server will go through that process again of trying to find that information. Having a too high time to live number will take longer for caching to flush and for your friends to be able to go to your glorious to-do app that's on Heroku. Having a too low TTL, then the server will be inundated with a high load and might not have the ability to deal with a higher query load. Another pain of propagation in TTL is that some internet service providers completely ignore TTLs and have their own expiry for records. Caching actually opens up the ability to poison a DNS cache. By far, this is not my area of expertise, but as I understand it, a DNS cache poisoning works like so. If a server doesn't validate a DNS response, like for instance via DNSSEC, someone could exploit that by essentially spoofing an IP address that he or she owns for a given hostname, forcing users of that certain hostname to be directed elsewhere. To be able to spoof a DNS entry, an attacker would have to create a faster response than that of a legitimate authoritative server. Now, you can effectively DDoS a DNS server, or a caching server, with probable non-cached entries, providing many attempts to send fake responses. Those random domains that are now cached aren't too useful, but what an attacker can do is include a name server in his or her response for the desired domain to compromise. So those are the potential issues with caching, and a lot of people actually do face issues with propagation when trying to deploy on Heroku. But I kind of wanted to go into the kind of cool, nerdy things that I did learn while exploring DNS, and maybe you will enjoy them as much as I did. So first off, I'll start off with interesting ways to interact with DNS. So previously, when doing a dig any queries like dig pyladies-t any, we noticed that we could not get any CNAME records back, like www.pyladies.com. You can certainly run a dig query against www.pyladies.com, but how many subdomains are there? You don't really know. Being able to look up a full DNS zone file is rarely allowed, but there's this tool called DNS map that literally brute forces a subdomain lookup. So trying to DNS map PyLadies, unfortunately only returns 4 results, even though I know that there's over 20. If you ever use this, don't expect the results to be comprehensive or fast, since it's literally searching based on a built-in or provided word list. So yeah, this tool is limited by a word list, but you can supply on your own a much longer word list if you want. So another thing that I learned when I was playing around with my DNS, I wanted to figure out what was cached locally on my own local DNS. So for Macs at least, I'm not sure for Linux systems or Windows systems, in order to find out what is cached locally, you literally have to kill the DNS process and send it to syslog. So after you run this command, after you flush the cache, and you go into your system.log on your system, you can see some familiar looking results. I heavily trimmed this so it actually looks kind of decent on the slides, but there's a lot more information. And interesting enough, all these entries were made from when I was DNS mapping Spotify. So it's pretty fun. If we actually look at a captured packet when I was using Scapy to sniff traffic generated by DNS mapping Spotify .net. You can see actually on the very top the Ethernet layer, and then the IP layer. which you can see it went from my computer IP address to my DNS router. And then the DNS map was trying out the zr.spotify.net at the bottom. And so you can see that question record that DNS will send. So I think looking through Scapy and sniffing DNS traffic is pretty interesting. But I'm hearing telepathically from you guys that not enough Python. So so here comes Twisted. So you can actually run a very simple DNS server with Twisted. Apologize again if it's not that readable. So this is a very simple DNS server. It is based off of ectresolve.conf, but you can supply your own DNS servers to dig through. And so we can run this, and as well as fire up Scapy and run the dig command against the server. And you can see the question down there when I was digging for python.org. It has a query name, type, and class, and it goes from my IP address, my computer, to my router. And so here's a response with the DNS resource record and the data associated with it. So we first had that question, and now this is the actual response. It went from my router to my computer. And you can see the resource record name at the bottom with python.org, the type, class, TTL, and data associated with it. All right, so we went over interesting ways to interact with DNS. Now some interesting ways to actually use DNS. Some of you folks may know the types of IP network addressing methodology, including unicast, multicast, broadcast. Anycast is a fourth one, where datagrams are sent from a single sender to a group of potential receivers, all identified by the same address, referred to as one to nearest association. And so Google actually uses Anycast for its public DNS servers, the 8.8.8.8 and 8.8.4.4, where someone looking up 8888 in Australia may go somewhere different than if someone in the US were to go to look up 8888. But they both receive the same information. So Google configures all its applications for Anycast and allows folks in operations to be able to take down one cluster at a time and reroute traffic to another. And there's no worry about folks not getting the same data when looking up 8888. And so it's quite nice for general load balancing. DANE stands for DNS-based authentication of named entries. It's basically a protocol for certificates to be bound to DNS names using DNS security extensions or DNSSEC. It's basically a proposed way to remove certificate authority for when a TLS client and a server authenticate. So I'm sure many of you are familiar with that lock icon on your web browser, but are you sure that you're connecting all the way to the website using the correct TLS certificate? It is quite possible and quite common for a firewall to get in between and terminate your TLS connection with the website and then recreate the TLS connection from your device to your browser. So you think that you're secure and you have an encrypted connection to your bank, but in fact the connection can be intercepted and the firewall or another device is able to see and potentially record all the interactions with the website. So if a browser supporting DANE detects that it is not using a specific or a specified certificate, it can warn you that your connection is insecure, even though you see that locked icon. And supposedly, the DNS Python library has support for this already in its development branch. Another nerdy nugget of awesomeness that I uncovered while my deep dive into DNS is it can be used for service discovery. There are a few ways and tools to implement service discovery, but it mainly boils down to what servers run this service. As mentioned, one can leverage DNS to help answer this question with the use of Srv Records. So Srv records within DNS zones map canonical names, typically in the form of underscore name underscore protocol, as you see here, .site, to host names. So for instance, at Spotify, each service has its own Srv record, with one record canonically named after the service itself. So when you spin up a Spotify client, it does an Srv lookup, similar to the dig command. And then the service lookup continues on. So a client connects to, or does an Srv lookup, it connects to an access point, and then it continues resolving to the data that's needed, either to playlist or storage or whatever. Last little nugget, which I think it might be the coolest little nugget, is the ability to store a DHT ring in DNS. DHT stands for Distributed Hash Table. A DHT gives you a dictionary-like interface or a key value store, but the data or the nodes are distributed among a network. Spotify stores some of its service configuration data within a DNS or DHT ring within a DNS TXT records. You may have seen TXT records elsewhere. I know that Google App Engine does some DNS mapping with TXT records. So data from a particular Spotify service is hashed and is locked at some point on a DHT ring. And the servers in the ring are responsible for a certain segment of the ring. In this case, instance B owns keys from 3F up into 14. And then instance E owns from C1 to 9E. It's kind of counterclockwise. It's a little bit confusing, but it's actually quite cool to use DNS in this distributed fashion. So I threw a lot of DNS at you, and DNS is by no means easy to get and to understand within like a 30-minute talk. So I guarantee you will F up your deployment configuration again, because DNS is hard. But it's not the only way, but it's not only hard to learn, but it's also hard to make a good talk. I was thinking like this talk is going to be crap, but it's actually DNS is crap. So hopefully you'll take some nerdy awesomeness away from this boring technology. And yeah, I hope you enjoyed the talk. These slides will be up soon, and thank you. I don't know how much time we have for. We have like a minute or 2 minutes. If someone, well, maybe I'll take one question, or maybe if you want a discussion, we could just go outside in the hall. Does anyone have a quick question, maybe? Yeah?
So, I know you were showing us a twisted DNS.
Yeah.
Making a DNS server. Like, if you just wanted to make your own DNS server, like from the protocol level up, just to play around and try to understand it better, how hard do you think that would be?
I think pretty hard, but I think it'd be fun. You'd probably have to investigate both like how Twisted implements it and DNS Python implements it. I know that that Spotify has its own kind of like resolver for like the service lookup. So I mean, so long as you kind of thoroughly understand the protocol, I guess, then it can't be too hard. But it should be a fun exercise, actually. Yeah. I think I'm out of time, but if anyone wants to catch me outside, then let's do that. Thank you again. Oh, yeah, I don't want questions.
Oh, okay.
Thank you. Can you help me with this?
Sure, definitely. Let me see what the best way is. I don't think I'm being of much help.